Hey, all you cool cats and kittens. This is your teacher, Mr. Forbes. Has anybody watched that series yet? The Tiger documentary? It's pretty crazy. I recommend watching it. All right, so we're on our day 5 of all the types of free responses that we have. Now, this day is purely dedicated to doing sequences and series. Okay, sequences and series. They've 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 taken a lot of questions from this, so tried to I think the questions we got are is going to have some stuff that you not need, but a lot of stuff you will probably need. So I got 3 free response questions we're going to try today, and some topics to go over. So I think the questions are pretty good. There's some, and I'm going to go ahead and tell you the questions that we do. All the free response topics, I think the sequence and series is by far the hardest one. I think that's why it's the last in the unit and why it's in BC only. These questions can just be very abstract sometimes. So take this with a grain of salt, take it however you want. But I'm just wanting to expose you to as much as we possibly can. I'm just afraid that they might give you something with sequences and series, so I want to be prepared for it. Okay. So let's do this. All right. I'm actually going to skip down to. I'm going to go ahead and summarize kind of everything we need to know real fast and then do some practice. So I kind of jumped down to slide 8 there if you want to go to that. But just to kind of refresh ourselves. Um, it, the questions that I sent y'all a link actually about what's going to be on the AP exam for this year. It looked like that it's not going to be calculator active, which is good because a lot of power series are not calculator active. Okay, so I don't know. You might see one of these on there. We'll see. This first bullet point here, I think you might need to know how to do, like write the Taylor-Maclaurin series for a given function. Usually to the first 4 terms, so we'll practice that. Um, and there's other methods of like substitution and stuff involved, and we'll see that in a few problems. I would still memorize the Maclaurin series for sine, cosine, e to the x, and your power series, which remember was summation n equals 0 to infinity of x to the n. And make sure you know the ones for the other ones as well. Okay. Find related series by substitution, differentiation, and integration, or adapting one of these, and we got some examples of that here in a second. I don't think you're going to have to worry about radius of convergence, but I know the topics that are in our unit is ratio test and alternating series test. And all of those are primarily used for is just identifying if it converges or not for the radius of convergence. I don't think you'll have anything with radius of convergence based off of the topics they took off, but again, we'll practice that some a little bit today. And as I'm doing the video, I'll try to really clarify which ones I think are topics that are still possible to be tested. Okay. Um, we are going to check endpoints today using ratio test, but we'll refresh ourselves on that. We do still need to know geometric series. So anything in the form a sub 1 times r to the n minus 1 power. And that converges if r is between -1 and 1. And remember, if it does converge, that the series is equal to the first term divided by 1 minus r if you're in this form. Okay. I don't think we're going to need to know many convergence tests. Like I said, just ratio test and alternating series test. You're not going to need to know this bullet point at all. Estimating error bound with Taylor, with Lagrange error bound, basically that last optional video. And I think this is a big important one here too, just to kind of make note of this one. Do not claim that a function is equal to its Taylor-Maclaurin polynomial. Like, if I asked for a Maclaurin polynomial for sine of x, that whole formula we had, okay, remember that this is only an approximation. Okay, this is only approximation. So, yeah, just keep that in mind. Okay. So, oh well, okay, maybe I should go ahead and write out. Okay, so this is the power series for 1 over 1 minus x. That's the Maclaurin series. Let's do the Maclaurin series for the other ones real fast. I'm just going to write out the general terms. Sine of x equals, and I'm just going to write out the summation part. So summation n equals 0, sorry, to infinity. And remember, sine's the odd function, so that's going to be negative 1 to the n, and then times x to the 2n plus 1 over 2n plus 1 factorial. Cosine of x is the same thing, but it's an even one, so remember that we get all the even power terms. So in order to do that, it's going to be x to the 2n over 2n factorial. And remember that e to the x is very similar to our power series, but it's going to be summation n equals 0 to infinity of x to the n over n factorial. I'd probably memorize all those still. Those are helpful to know. If you don't know those, and it's required from the start of the problem, you're not looking too good. Okay. All right. So let's go back to looking at our first free response question here. This is from 2010. This is BC number 6. Okay. And a lot of times it would be like a BC like number 6 or 5, something calc inactive. Okay. All right. So let's just go through each piece and kind of see some stuff. And again, I'm going to try to shorthand as much of it as I can. So pause it, try to work it out as much as you can, but we'll see. Okay. So it looks like we got a piecewise function here for f of x, and it looks like we got a function here for g of x, which is equal to 1 plus the integral of f of x. So just keep those in mind. And part A says, write the first three non-zero terms and the general term. So we're going to have 3 terms adding together plus the general term for a Taylor series for cosine of x about x equals 0. So there you go. From the very beginning, all it wants you to do, and all it's testing you, is do you know what the Maclaurin series is for cosine? If it's centered about x equals 0, it wants to know the Maclaurin series for cosine of x, which I just wrote down. Okay, so there's some gimme points right there if you can memorize these. So cosine of x is equal to, and the Maclaurin series, so the first 3 non-zero terms, which if you just hopefully memorize that it's the even terms, we're going to start off with x to the 0 power, or just 1. Okay, and then it goes minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6 over 6 factorial and so on, minus plus negative 1 to the n. Remember we said it was x to the 2n over 2n factorial. So there's your first 4 terms, or I'm sorry, your first 3 terms and the general term for cosine of x. And in part A, we're going to use this series to write the first 3 non-zero terms and the general term for f about x equals 0. Okay, so this is for cosine. F is defined as cosine of x minus 1 over x squared for pretty much every value that's not equal to 0. So what it's saying, and we've done this before, is if I want to use this to create the power series for this, notice how it's the same thing, but just minus 1 divided by x squared. So what I'm going to do, and I would write this all separately, but I'm going to, for sake of time, I'm going to say I'm going to take this function, I'm going to subtract 1, and divide by x squared. And that's how I get it for f of x. So f of x, okay, is equal to, if I subtract 1 from this whole quantity, it's going to cancel out this one, okay? And if I divide by x squared for all the quantities, it's going to reduce these powers by a power of 2. So that's going to be x squared, that's just going to be x, and so forth. Okay. So if I were to simplify this all down completely, x squared divided by x squared is just 1, so that's going to be 1 over 2 factorial plus x squared over 4 factorial. If I would have gone to the next term, it would have been, I'm sorry, and that should have been negative 1/2. If I go to the next term, it would actually be minus, it would have been x to the 6th divided by x squared, so x to the 4th over 6 factorial. So if I were to write the general equation for that, it's still alternating, but it's alternating at the first term's negative, so that's actually negative 1 to the n minus 1 power. And what's happening with x is, if you think about it, x is going to be, so look, oops, x is going to be, if you think of this as like n equals 0, 1, 2, if we relate that, x is still being done to the 2n power. Okay, so if this is 1, this is 2 times that. If this is 2, the x to the fourth is 2 times that. Over, and then how's the factorial working? Okay, well, it's still going to be, let's see, it looks like it's going to be 2n plus 2, I think. Yeah, because if I take any of these terms and multiply it by 2 and add 2, I would get that correct factorial. And I think that's kind of a hard part sometimes, is trying to figure out that pattern, but just kind of messing with it until you get it. But there you go. So okay. So we're going to come back to this. We're going to need to know this. This is the Taylor series centered at 0, which is the Maclaurin series, for f of x, as defined above. Okay, we used cosine and we built it up by subtracting 1 and dividing by x squared. Okay? All right, so that was the A. Let's move on to B. What's B say? B says use the Taylor series for f about x equals 0, which, hey, I just came up with in part A, found in part A, to determine whether f has a relative maximum, relative minimum, or neither at x equals 0, and give a reason for your answer. Okay. This is kind of a stretch for this one, and I want to make sure I can explain this pretty well here. Okay, so for B, we have a max, a min, or neither. Okay, we need to look at f prime of x. Okay, f prime of x, and at 0. So what's the best way to say this? If I were to do, all right, okay, I'll explain it this way. F prime of x, okay, oh, I'm sorry, we're doing it at 0, so f prime of 0, okay, because I'm trying to figure out if I have a max, a min, or neither at x equals 0, so I need to consider f prime of 0, right? That's how we deal. Let's just think of the basic terms here. We find a max, a min, or neither at a certain x value by looking at the derivative value there, okay? Well, remember with a Taylor or Maclaurin series that f prime of 0 is the term in front of your x value in the Taylor series, right? Based off the Taylor series definition, it goes f plus f prime of 0 times x over 1 factorial plus f double prime times x squared over blah, 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 okay? So in this particular case, if you notice in part A here, there is no x term, which means that this value right here, all right, was equal to 0. Okay, and we knew that already dealing with cosine. We knew that the f to the first derivative, when we first did this, we knew that it went to 0 because f prime of 0 is equal to 0. We know that. Okay, so I know that 0 is a critical point. Okay. Well, let's consider f double prime to figure out what's going on at that critical point. Okay, which, think about it. F double prime, based off of our definition of a Taylor series, is the number that goes in front of my x squared term. Okay, the number that goes in front of my x squared term. So remember, remember that it's x squared over 2 factorial. It's the number that's in front of that. Well, I know that my x squared over 4 factorial, that is my term where the second derivative is at. So if I want to know what the second derivative is equal to, okay, I know that that x squared, so that f, let's see, f double prime of 0 over 2 factorial times x squared, I know that from my Taylor series is equal to x squared over 4 factorial. So I can actually solve for what my f prime of 0 value is equal to. Okay, this is all based off of what I know about Taylor series definition, and then just using first and second derivative knowledge. Okay. Well, solving for f double prime of 0, the x squareds cancel out, and I can multiply both sides by 2 factorial. That ends up being f double prime of 0 equals 2 factorial over 4 factorial, or 2 over 24, or 1/12. Okay, so f prime of 0 is equal to 0, and f double prime is equal to 1/12. So that means I have a critical point that's concave up. So what happens when that's the case? It means we have a relative minimum. So we can actually say by the second derivative test, x equals 0 is a relative minimum. That's whenever you are concave up, because think about it, here's my point. I know it's a critical point and it's concave up, so that must make it a minimum value. Okay. So I think B was a very hard problem conceptually, because you had to think about, all right, I have to use a second derivative test because I got to figure out f prime of 0 and f double prime of 0. And how do I find those values? Well, I had to use my knowledge of what Taylor series, how they were created, to figure out what those values were equal to. So it was a tough problem. I really believe it was a tough problem. Okay. I think I'm gonna have to make a new slide here. Okay. Let's go on to C. All right, hopefully you're looking back at your own paper or your own notes, but I can switch back real fast. C says write the fifth degree Taylor polynomial for G about x equals 0. That's not too bad. Okay. All right, so I'm looking at my paper now. It says write the fifth degree Taylor polynomial for G about x equals 0. All right. Fifth degree Taylor polynomial, so that's to the fifth power, right? Well, what is G equal to? G of x is equal to, from the problem, 1 plus integration 0 to x, all right, of f of t dt. All right. Now, it wants me to create the Taylor polynomial for this to the fifth power. So all I got to do is create the Taylor polynomial for this part, and I'll have it for g of x. But I already know what the Taylor polynomial for f is. So all I got to do is integrate the 1 for x, okay, and then add 1 to it. So let's write that out. So from part A, we know this is going to be equal to 1 plus, okay, and the Taylor polynomial from part A for f of x was, and I'm going to be integrating this, let's say 0 to x of, from part A, we got that it was negative 1/2 plus, and I'll put t in instead of x. Let's say plus, it was t squared over 4 factorial, and then minus t to the 4th over 6 factorial. Okay. And I'm going to stop right there, because if you think about it, it's saying in part C, write the fifth degree Taylor polynomial. So I need to go to the fifth degree. And because I have fourth degree right here in the integral, I know that that integral is going to go to a power of 5. So now all I have to do is just simplify this. And I have the Taylor polynomial for g of x to the fifth degree. So what this is equal to, okay, is 1 plus, we're going to integrate each of these. So integrating negative 1/2 is going to be negative 1/2 x, all right, plus integrating t squared over 4 factorial is going to be add 1 and divide, so that's going to be x cubed over 3 times 4 factorial, and then minus, I'm going to add 1 power and divide, so it's going to be x to the 5th over 5 times 6 factorial. Okay, and we don't even need the parentheses at this point, so we got that it's 1 minus 1/2 x plus x cubed over 3 times 4 factorial minus x to the 5th over 5 times 6 factorial. And this is calc inactive, so I'm not gonna multiply that out. So there's my answer. There's the Taylor polynomial for g of x to the 5th power. And you notice in part A, part C here, all we did was take cosine functions and pretty much build it up a little bit. That's all we did. Okay. And now part D. So part D says, look back together. Part D says the Taylor series for G about x equals 0. Okay, so literally the function that we just came up with, evaluated at x equals 1. So now we're actually going to plug in a value for x. It's going to be evaluated at x equals 1. Is an alternating series with individual terms that decrease in absolute value to 0. So it says you, and so pretty much it's saying, hey, we got an alternating series here that converges. Okay, so use the third degree Taylor polynomial for G. So third degree Taylor polynomial for G. I only need to go to the third degree for G about x equals 0 to estimate the value of G of 1 and explain why this estimate differs from the actual value of G of 1 by less than 1 over 6 factorial. All right, easy enough. So let's do this one together. Okay, so D. So I'm going to estimate G of 1. I'm going to first estimate G of 1 by using the Taylor polynomial to a power of 3. So it's going to be 1 minus 1/2 times 1 plus 1 over 3 times 4 factorial. Okay, or 1 cubed, and that's to the third degree. Okay. All right, so if I simplify that out, that's 1 minus 1/2 plus 1 over 3 times 24, 3 times 24 is 48, 60, oh wait, 72? 24, 48, yeah, I don't know why I had such trouble with that. Anyway, and I did actually simplify this fraction down. I don't think you'll have to since it's not calc inactive, but I did do it over here on my paper. 37 over 72. Okay, so that's the approximation of what G of 1 is using the Taylor polynomial, okay, that we estimated it with. Now, it wants us to, this is the part that's probably not, you're not going to be tested on because it's wanting me to do the alternating series test for estimating the error, and I don't think any error bound is going to be on your final exam, but I still think it's a pretty good thing to test out. So it wants me to show that this value differs by no more than 1 over 6 factorial, like I said from the problem. Okay, so we know by the error bound for alternating series, and I've wrote this out a few times. We know that the infinite sum, subtract my approximation, which in this case is 37 over 72. I know that that difference is going to be no more, it's going to be less than or equal to the value of my next term. Okay, which that is equal to, my next term in the sequence is actually going to be whatever 1 over 5 times 6 factorial is. Okay, so that's going to be 1 over 5 times 6 factorial. So I know that the difference between my approximation and S is less than or equal to my next term. And this value right here is actually less than 1 over 6 factorial because this is a bigger denominator. So we indeed just showed it using the alternating series error bound test. Okay, that's all we needed to do. So I wouldn't worry about D as much as this part of D. Everything else, building a function, I think that's something you definitely need to know how to do. So I think that was a good problem. So anyway, here's the answer key to it. Like in part A, we came up with the cosine. All right, we did the terms in cosine. We built the function, okay, by subtracting 1, dividing by x squared. So we got the first 3 terms in the general term. Our explanation, so I think B was kind of the hardest one in my personal opinion. Having to make that relationship between f prime as the coefficient of x and f double prime over 2 factorial as the coefficient of x squared, and solving for each of those values. So we got f prime of 0 is equal to 0 and f double prime of 0 is equal to 1/12, and therefore we were able to use the second derivative test. So figuring out f prime of 0 and figuring out your answer with a reason, that could be tough. I get that. And then C says, C was figuring out G, so it was just getting 2 correct terms and then getting the remaining terms correct. So we got that. Figuring out your estimation for G using the up to the 3rd power. So we use these 3 powers here. And then then pretty much coming up with our alternating series error bound. So our explanation in that case. Okay. So there we have it. Let's go on to another problem. All right. I like this problem. I think this is a good one. It's using e to the x now, so we know what e to the x is. Okay. So the Clarence series for e to the x. So now it's not requiring you to memorize it. Okay, it's actually telling you what it is. It's saying, all right, e to the x is equal to 1 plus x squared over 2 plus x cubed over 6 plus, and we should hopefully know this by now, but here it's written for us. E to the x is just x to the n over n factorial, the summation of that from n equals 0 to infinity. All right, and it's also telling us that we have some random continuous function f that's defined by this, okay, which has e in it for every value but 1, and f of 1 equals 1. So the function f has derivatives of all orders at x equals 1. All right, part A. Part A says, write the first 4 non-zero terms, so first 4 terms, and the general term for the Taylor series x to the x minus 1 squared power about x equals 1. Okay? And yeah, I mean, so think about it. Okay. We got the Taylor series right here for e to the x. Okay? If I want the Taylor series for e to the x minus 1 squared, okay, all you have to do is plug in x minus 1 squared in for x into your e to the x. We're building up the function just like we did for the cosine function in the last problem. Okay. It says that this is centered about x equals 1, which is accounted for right here in the x minus 1 power. Okay. So all I'm going to do is I'm going to say that e to the, and it wants us to do the first 4 non-zero terms. So e to the x minus 1 squared power is equal to, so everywhere I see an x in the e to the x, I'm going to plug in x minus 1 squared. That's how you build a function from those 4 functions that we know the Taylor series for. This is going to be 1 plus. Instead of x, I'm going to have x minus 1 squared plus. Instead of x squared, I'm going to have x minus 1 squared squared, or to the 4th, over 2. And then plus x minus 1 cubed, or squared cubed, which is to the 6th power, over 6. And there's our first 4 terms, and now we need to have our general term. Okay, so remember how we come up with our general term. This is n equals 0, 1, 2, and 3. And we need to think about what's happening as our pattern is continuing. Okay, so I would say that this is going to be actually on the top. It looks like it's going to be x minus 1 to the 2n. All right, you can think about what happens as I plug in 1, 2, and 3 into that. That's how I get the top. And on the bottom, it looks like it's going to be, still looks like it's going to be n factorial. 0 factorial, 1 factorial, 2 factorial, and 3 factorial. Okay. So there we did. All we did was just build the function from what we had previously. Okay. Not too bad. All right, B. B says, use the Taylor series found in part A. Okay, so we got the Taylor series in part A. Good. To write the first 4 non-zero terms and the general term of the Taylor series for f about x equals 1. I want the Taylor series for f about x equals 1. Okay, so what you notice is in f we already have that first portion right there. We already have that value. Okay, we built that in A. Now to build f, all we got to do is subtract 1 and divide by x minus 1 squared. Okay, so for sake of room, I'm going to go ahead and kind of write that out. Okay, I'm going to say, all right, if I take the answer that I got in part A, okay, if I take that answer and I subtract 1, what's that going to do? It's going to cross off that first term. So then I'm left with x minus 1 squared plus x minus 4 to the 4th, sorry, what am I saying here? X minus 1 to the 4th over 2 plus x minus 1 to the 6th over 6. And I'm supposed to go to the first 4 terms, so let me go ahead and go to the next one. It's going to be plus x minus 1 And if I follow that pattern, that's going to be x minus 1 to the 8th power, because it goes 2, 4, 6, 8, over 4 factorial, or 24. Okay. But then I got to divide by x minus 1 squared. So I'm going to divide all this quantity by x minus 1 squared. And what that comes out to be, all right, I'm about to sneeze, I can feel it coming. If I divide all these by x minus 1 squared, this is going to go to 1, plus this is going to go to x minus 1 squared, excuse me, x minus 1 squared over 2, plus x minus 1 to the 4th over 6, I'm running out of room here, plus x minus 1 to the 6th over 24, plus dot, dot, dot. And the general term for this, is, again, if you think about this as n equals 0, 1, 2, 3, you think about the pattern, I believe it's going to be on top, it's going to be x minus 1, all right, and to the power of, let's see here, it looks like 2n, actually. Okay, so same as before, that hasn't changed from part A. And then divided by, okay, what's going on down here? So let's see, it looks like n plus 1 factorial, I believe. Looks like on bottom we have n plus 1 factorial. Yes, that's what we're getting. Okay, so there is your first 4 non-zero terms and the general term for the f function. Okay, and we built that from our e function from the very beginning of the problem and from part A. Okay. So then C says use the ratio test to find the interval of convergent. Now C is probably not going to be tested. Okay, interval of convergence is not going to be tested, but we're still going to practice it just for the heck of it to figure out the interval of convergence for the series that we just came up with in part B. Okay, so this is what I'm going to do. I'm going to try this out real fast. I think this is going to be cool. Here we go, here we go, here we go. Boom. I'm going to do that. I'm going to go to, dang it. Dang it. I was trying to be cool. This isn't as cool as I thought it was going to be. Oh my god. I just want to copy this to the next slide. Oh my god. It's not going to happen, is it? Let's go boom, boom, boom. Darn it, all to heck. I'm going to try one more time and then I'm done. Boom, boom. Okay. Control copy. I'm going to go to the next slide. Ha ha ha. Insert. New slide. I'm going to go to control. Oh, that's not good. All right, I'm really excited about that. Sorry. All right, I already forgot what we're doing. We're doing C. Remember, C says use the ratio test. Okay, use the ratio test to find the interval of convergence for this Taylor series right here. I want to know what this interval of convergence is. All right. Remember how it works. Remember how interval or ratio test works. Now, ratio test is not going to be on there in terms of finding interval of convergence, but it did say ratio test would be on there in terms of just identifying convergence. Okay, so not the radius of convergence, but if a function without x in it, if it converges or not. So we can still practice that. And remember, we use that with ones that have like power of n and factorial in the problem. So this will be good review. Okay. All right. So remember how ratio test works. Limit as n approaches infinity of absolute value of a sub n plus 1 divided by a sub n. Okay. So in this case, that's going to be the limit as n approaches infinity of the absolute value of. Okay. So a sub n plus 1 is going to be x minus 1 to the 2n plus 2 power, if you distribute, divided by n plus 2 factorial. And I'm going to go ahead and do same change flip when I'm dividing by a sub n. And I'm going to say that this is going to be n plus 1 factorial over x minus 1 to the 2n. Okay. All right. Now, when we're simplifying this down, remember how this works. So like x minus 1 to the 2n and x minus the 1 to the 2n cancel out. And on top, I'm left with just x minus 1 squared. Okay. And remember how n plus 2 factorial can be written. That's n plus 2 times n plus 1 factorial. So those cancel. So I'm left with n plus 2. Okay. So if I take this limit right here, as n is approaching infinity, if I take that limit, remember, there's a higher power on bottom. There's no n's on top. So no matter what, this equals 0. No matter what I plug in for x, this limit will always equal 0, which is less than 1. So that means that no matter what value I plug in for x, remember how we talked about this, no matter what value I plug in for x, it's going to converge for any number. So the interval of convergence is actually equal to negative infinity to infinity. Any value of x is going to make this converge. You can test any point you want in that series for x, but it's going to converge. Okay. There you go. And then I think I can squeeze part B on here. D says, let's go back together. D says, use the Taylor series for f about x equals 1. So what I found in part B here, to determine whether the graph has any points of inflection. So the graph has any points of inflection. So essentially what I'm going to do is I got the function right here, okay, and I need to look at the points of inflection, so I need to look at the second derivative. So if I got what f is approximately equal to, I'm going to come up with its derivative. Okay, so remember this is the I'm going to figure out any points of inflection for this series right here. Okay, so let's first take the derivative. So like f prime of x is equal to derivative of 1 goes away. This would be 2 times x minus 1 oh, I just realized this didn't copy that. I was about to say this didn't copy the 2 or the 4, right? No, this was a 6. 2 and a 6. They didn't copy those numbers. That's weird. I must have missed that whenever did I miss that when I copied it? Dadgummit, I did. Okay. Anyway, so that's 2. Okay, then over 2. I thought those 2's canceled. They do. And then plus, okay, so the derivative of that next term is going to be 4/6 x minus 1 to the third, and then plus 6 over 24 x minus 1 to the fifth, okay, and then plus dot 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 plus. Now if I take that derivative, it's 2n x minus 1 to the 2n minus 1 power. That's just power rule over n plus 1 factorial. And now the second derivative is going to be equal to, the derivative of this is just 1, plus 4 times 3 over 6 times x minus 1 squared plus 6 times 5 over 24 x minus 1 to the fourth plus dot 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 plus. If I take that derivative, that's 2n times 2n minus 1 x minus 1 to the 2n minus 2 power now, after doing power rule, all divided by n plus 1 factorial. Okay, so there's my second derivative. And when we have points of inflection is where this is equal to 0. Okay, where this is equal to 0 for x. Okay, now because, here's my explanation here. All these terms are quantity squared. All these terms are positive and quantity squared from here on out. So anything past the second term here, all these values are always going to be positive. So there is nothing. So f double prime of x is greater than 0 for all of x. There's no point for x at which I'm going to have a negative number or 0. So therefore, there are no points of inflection. All right, no points of inflection. Oof, looking at this is a mess, but I'm telling you, this is some hard stuff, but hopefully you're not going to get tested on, well, you might get tested on points of inflection, I don't know, but definitely not this part of it, the interval of convergence. But like here, for instance, okay, so here's your answer key here. All right, for like part A, we came up with the first 4 terms, okay, in the general term, that was for e to the x minus 1 squared power. Then we figured it out for f, the first 4 terms in the general term. Okay. Then we set up the correct ratio test. We figured out the limits of the ratio, okay, which was this part right here, and got it equal to 0. And then we got our answer was infinity to negative infinity. And then we took the second derivative and we figured out the answer based off the fact that the second derivative is always greater than 0. Okay. Tough problem. And now I got one more. Okay, one more. I like this one. I think this is again another good one here. It's talking about some error bounds again, but I think it's like I think part A is the most beneficial for y'all on this one because we're using ratio test again, but you're not gonna have to do it to find the interval of convergence, but you are gonna have to use ratio test probably for just seeing if something converges. So this is still a good practice of that. Okay, so here for part A. All right, remember ratio test is the limit n approaches infinity of a sub n plus 1 over a sub n. So I'm going to say, all right, we're doing it for this one right here. Remember, if there's a negative 1 to the n involved, ratio test is absolute value, gets rid of that. So the a sub n plus 1 is going to be x, all right, to the 2n. It's actually going to be 2n plus 3 power if you distribute the n plus 1 through, over 2n plus 5, actually. Okay. And then multiply by, we're going to do same change flip for a sub n. It's going to be 2n plus 3 on top and x to the 2n plus 1 on bottom. Okay. Now, if we simplify this out, it looks like the only thing that simplifies is x to the 2n and x to the 2n. So I'm actually left with the limit as n approaches infinity of the absolute value of x cubed 2n plus 3 over x to the first 2n plus 5. Which if I take that limit to infinity, it looks like that we have the same power on top and bottom, so I'm taking the leading coefficients, which is all of this right here. So I'm left with 2x cubed over 2x, which simplifies down to just x squared. So I'm trying to solve for that interval of convergence, which if I do, remember all I gotta do is take the square root, and that doesn't affect anything with this, so I just know that any value that makes this inequality true is between -1 and 1. Okay? So there's my interval of convergence for part A. But remember what we said. We don't know if the endpoints are included or not, so we always have to test those points. So this is going to be good practice for y'all as well, I think. So I'm going to test -1, so I'm going to let x equal -1, I'm going to test that. I'm going to say, all right, let's do the summation n equals 0 to infinity of -1 to the n, x, which we're now making -1, to the 2n plus 1 power over 2n plus 3, okay, which actually equals, on top, it's -1 now to the 2n plus 2 power, okay, because we just combined those bases together, and then over 2n plus 3. So we're trying to identify if this is actually part of the interval convergence. We're trying to identify if this converges. Well, we know how to do that. Well, this is one of the tests that we actually need to know is the alternating series test. I see the alternating series piece, so I'm just going to consider the a sub n. Remember, we had 2 pieces we had to talk about. Number 1, we had to discuss that the limit as n approaches infinity of a sub n actually equaled 0. So that's the limit of 1 over 2n plus 3, which is definitely equal to 0. So that first part is true. And number 2 was to identify that a sub n plus 1 was less than a sub n. So ultimately that it's decreasing. And we did that by doing the derivative. So we said that like a n's, which we'll call f of x, remember we called it f of x, we'll say f prime of x is equal to, so the derivative of 1 over 2n plus 3 is going to be negative 1 over 2n plus 3 quantity squared times 2. Okay, so just doing a little bit of chain rule there. Okay. All right, and that value is always going to be negative, so it's always decreasing. So therefore, we're good. Okay. So that means that we include negative 1 in the interval. So let's now test x equals 1. Okay. And it's going to be the same type of setup. It's going to be n equals 0 to infinity. We're doing negative 1 to the n. And I just realized here this was n right here, so this should have been actually 3n plus 1, but still, it's still an alternating series test, so that worked out good for us. But anyway, over here it's going to be negative 1 to the n, and this is going to be positive 1 to the 2n plus 1, which remember that just cancels out because 1 to any power is 1, and over 2n plus 3. Well, this is the same exact setup as the one with x equals negative 1. It's still an alternating series where a sub n is equal to 1 over 2n plus 3. So the alternating series test is going to yield the same results, so therefore it does converge at 1. So my interval of convergence is actually negative 1 to 1 inclusive. Okay? All right. I ran out of room doing part A, so we're going to just go on to the next slide to do part B. It says the Maclaurin series for G evaluated at x equals 1/2 is an alternating series whose terms decrease in absolute value to 0. The approximation for G of 1/2. So we're not given G explicitly, but it's telling us that the approximation for G of 1/2 using the first two non-zero terms, which are these two terms right there, x and x cubed. I'm saying if I plug in 1/2 for x, they're telling me right now that it's 17 over 120. Show that the approximation differs from the actual value by less than 1 over 200. Easy enough. If I'm wanting to approximate error for alternating series test, remember that the way we do that is actually to say that the absolute value of the sum minus the partial sum is less than or equal to the next term in the list. Easy enough. I'm saying that, okay, so my actual sum, which we're approximating the actual value for G of 1/2, I'm saying that this value here, okay, minus my partial sum with the first two terms, it told me it was 17 over 120, yeah. I know that's going to be less than or equal to the value of the next term. Well, what's the value of the next term? It is x to the 5th over 7, which is 1/2 to the 5th over 7. Okay, and that value, if I simplified it out, that's 1 over 32 times 1 over 7, which is, I got to be 1 over 224, and that value is less than 1 over 200. So we just showed that the error is definitely less than 1 over 200. And that's just using the error bounds for the alternating series test. Okay. And then lastly in part C, it says write the first three non-zero terms and the general term of the Maclaurin series for G prime of x. All right. So we got G prime of x is given right here. It's x cubed minus it's x over 3 minus x cubed over 5 plus x to the 5th over 7, and we got the general term here. So I'll let y'all kind of write that down and go back to it if you need it. But if I take the derivative of that, not bad at all. Take the derivative of x over 3, that's just 1/3. If I take the derivative of, I'm looking at my paper here, x cubed over 5, that's going to be 3 over 5x squared. And if I take the derivative of x to the 5th over 7, that's going to be 5/7 x to the 4th. Okay. And then minus, dot, dot, dot. All right, what's the general term going to be? All right. Well, let's think about it. Okay, what's the pattern going on here? Okay, this is n equals 0, 1, 2. Let's think about what that pattern looks like. And it can be as simple as just literally taking the derivative. And honestly, that's what I'm going to do. I mean, okay, you can just take the derivative of the general term in part A, but we can also identify the pattern here. Okay, on top, it's going to be 2n for it's going to be 2n plus 1 on top. On bottom, the number is going to be, that looks like 2, see, 3n plus 2, I think. No, 3n plus 1. No, 2n plus 3. Yeah, that's going to be 2n plus 3 for the number on bottom. X, how x is working is, it looks like it's going to be 2n, x to the 2n. And then also we're alternating, so we got to have that -1 to the n power. Okay. So there you have it. There's the first 3 terms of g prime and the general term. So notice how a lot of problems are practicing like finding those terms and being able to find a general term here too. Okay. All right, well, let's see. Dude, number A was worth 5 points. My goodness. Okay, we set up the ratio test. Okay, we did the ratio test. We figured out the limits. We got it to be x squared. We identified the interior to be -1 to 1. We considered both endpoints and determined that they were convergent at the endpoints. We got the final answer. We used the error bound for number 2 and figured out the error. And we found the first 3 terms and the general term for the last one. So guys, I'm not sure what else to tell you as far as alternate or sequences of series goes. I mean, they cut out a lot of it, so I don't know how much of this is going to be on there, is not going to be on there. But again, I would memorize these 4. Okay, so those 4 representations of our Maclaurin series. I would again, the stuff we need to know. I would know alternating series and ratio tests. So I would know alternating series, which I wrote right here, alternating series and ratio test. I would definitely know that. And I mean, that's about it. Maybe no geometric as well, geometric series. So I wrote that right here. And maybe no harmonic series and p series. So 1 over n to the p power. Maybe know that. Summation n equals 0 to infinity. And remember the harmonic series is just 1 over n. But I think that's about it, really. So good practice problems, see what you can do. And that does it for all the types of sequences that are types of free responses that you might see. Starting next week, we're going to just be practicing from year to year. And I think I'm going to start with 2014 on. So, good job, guys. Bye.